Hey, hi everyone. Welcome to Sigmoid Tech Talk. My name is Ankit Sharma and I'm working as an associate lead data scientist at Sigmoid. Today we are going to discuss about regularization. It is one of the very important techniques in machine learning field. Let's not waste our time and go in the slides. So as we discussed in the previous sessions, how we come at this best fitted lines using gradient descent and convergence theorem. But while building our machine learning models, we can face a problem of overfitting or underfitting. Now to come up with uh, these solution of these problems, overfitting, underfitting, there's one technique called as regulation techniques. So what is regulation techniques? Regulation technique is nothing but it is a way of calibrating your machine learning models to minimize your cost function to prevent overfitting and underfitting. Here I have shown an example of overfitting where in this graph I am showing this green dots as an actual data points and this black dotted lines is coming from our machine learning models. If you see, this black dotted line is passing through each of the actual data points, and this scenario is called as overfitting. Now, to solve this overfitting, we applied some regulation techniques and we got this graph. If you see this blue dotted line, now our model is providing the optimal solution, and this is how regulation techniques help us. Now there are mainly two major types of regulation technique. The first technique is called as rigid regulation. The second is called as the lasso regulation. We are going to discuss in detail about these two techniques. The first one is the rigid regulation, or it is also called as the L2 regulation. So the cost function of rigid regulation is given by this function, which is we have shown here. This is coming from the linear regulation cost function, where it is summation of your predicted minus actual value whole square. And this is added, this is the penalty terms which we are adding for rigid regulation, which is nothing but lambda times your square of your magnitude of your coefficients. So this complete function becomes for rigid regulation. Now, what happens in rigid regulations? Your beta coefficient is going to get penalized, and it is going to shrink your beta coefficients and bring those values uh, closer to zero if it is not making any significant impact in your predictions. For example, let's say you want to predict the price of any house, right? So let's say price is your dependent variables which you want to predict from your models, and there are certain parameters or variables which will decide the price of your house. The first parameter is the location of your house, that is the first variable. The second variable is your area of your house, and third variable is the color of the house. Now let's say all these three beta coefficients of variables are very high. Now, what rigid regulation will do, it will try to minimize or it will try to shrink the bigger coefficients which is having very high value, and for any variable that is the color of the house, it is not making any significant impact in the price of the house. So what is rigid regulation is going to do, it is going to shrink a lot and it will try to make it close to zero. It will not make the beta coefficients of color value variable to zero. It will try to make the variable very close to zero. So this is what regulation technique does. And one thing to be noted here, if you keep the lambda value as zero, so this term will become zero, and the remaining term, which is this term, will be left for the cost function, which will resemble the linear regression model. So this was all about the rigid regulation. Now we will going to discuss about the lasso regulation techniques. So lasso regulation techniques is also called as L1 regulation techniques, and the cost function of lasso regulation is given by the summation of your predicted minus actual whole square plus the penalty term, which is lambda times absolute value of your magnitude of your coefficients. Lasso regulations full form is least absolute sinkage and selection operator. It is called absolute sinkage because here also your beta coefficients is going to shrink and it will come close to zero. And it is also called selection operator because if any variables, that is for example in the previous example which I gave in the rigid regulation, the house price, right, at that point a color variable was not making any significant impact and it was not very important variables. At this point it is going to put the beta coefficient of color variable as zero. It is not going to just sync it is going to put at zero only. So this is the main difference between rigid and regulation techniques. Here, it is going to penalize the beta coefficient and put them to zero, and as well as it is going to sync those variables. In this session, we are going to discuss about the limitation of regulation techniques and also discuss the important parameter that is lambda, which comes in the cost function. Let's go in detail and discuss about the limitations of regulation techniques. So the cost function of rigid regulation and the lasso regulation is given by this formula. The main difference we have already discussed is the penalty terms. Here it is lambda times the beta coefficient square. It is the absolute value. Coming to the limitation of rigid regulation, the first limitation is it is not good for feature selection. What does it mean it is not good for feature selection? It means that it is not going to put your beta coefficient value as zero. Whatever number of independent variables you are going to have in your model initially, the number of variables remain the same, and that is why it is not helps in the feature selection of your model. The second limitation is the model interpretability. So as you are going to keep all the variables in your models, irrespective whether they are important or not, it creates a problem why you are interpreting your model. So that's the second limitation of rigid regulation. Now coming to the lasso regulation. So the first limitation of lasso regulation is problem with certain types of data sets. For example, if you are having 10 number of records in your data set and you are having 15 number of variables. So what lasso regression will do, it will penalize the beta coefficients, higher beta coefficient value, and but at the end it is going to keep at least 10 number of variables in your model, and it is not going to put beta coefficient zero either if even if the variables are not important for the prediction. So that's the first limitation of lasso regression. The second limitation of lasso regression is the multiclonality. For example, if you have two variables in your models and they both are highly collinear variables, so lasso regulation is going to eliminate any one variable randomly and keep only the remaining variables in the model. Now it creates a problem. Let's say if you want to keep any particular variable in your model for the prediction, at that point of time you are going to face this problem. So this was the second limitation of the lasso regression. Now we are going to discuss about the importance of lambda values. So as we seen, the lambda value comes in the cost function of this both rigid and the lasso regulation techniques. The importance of lasso this lambda value is it helps us to penalize, or it gives us the flexibility how much we want to penalize the cost function. So that is the main importance of lambda value. For example, if you see here we are having very low value of lambda. So at this point, if you see this blue line represents the cost function or the loss value of your training model. This red line represents the cost function or the loss value of your cross validation model, right? If you see at this point of time, you have very less value of your train model. And if you see at this point of time, you have cross validation error very high, right? So this scenario is called as high variance scenario, and at this point of time your model is overfitting, which can be seen from this point. Here your red dotted line represents your actual data points and blue is your fitted model, right? So this, if you see, your blue line is passing through each of the data points, so this is called overfitting of your model or high variance, and this happens when you are having very less value of lambda. Now, if you keep on increasing the lambda value, and you will come here at this point of time. If you see at this point, you are having very high value of your loss function for trained model, and at the same time, you are having very high value of your loss function for cross validation model. Now, this scenario is called as high biasness, right? This can also be shown in the below graph where the same blue line is not passing from each of the red data points. This is also called as underfitting. So wherever you are having very high value of lambda, your model might face underfitting issues. So that is also avoided. So both high variance and high biasness or overfitting or underfitting should be avoided for an optimal solution. Now, if you see this point, this particular point, you are having very low value, the least value of your cross validation model, and your training model is also less. So this is the very right value of lambda, at, and this point is called as the optimal value of lambda. So ideally, your model should be at this value of lambda, and this point is called as, or this whole scenario is called as the bias variance trade-off. You can also see the graph at this lambda value. You can see this model is correctly right fitting, or your line is passing very accurately from each of the data points. So this is the best scenario. So this was all about your regulation techniques. So we discussed what are the two different types of regulation techniques, the limitations and the importance of lambda. So this was all about regulation techniques. Thank you everyone for watching the video. All the best. Thank you.